All right. Okay, so if you didn't understand what I was describing, don't worry, it's not that important. What's important is that f of u would describe the flux, the amount of conserved material that passes through a certain point per unit amount of time. And if the differential equation can be written in such a way, then you can start working out the integral form. The integral form is just integrating this equation over an arbitrary interval a to b. And the time derivative of the total amount of conserved stuff in this interval would be equal to f of u a minus f of u b. This also makes a lot of sense from a conservation point of view, because the time derivative of the total amount of conserved stuff within the interval would be equal to the speed at which stuff flows from the left interval, flows through the left interval A, left point A, minus the speed at which the material flows out of the domain at the point B, right? So basically, this is A, this is B, then the flux over here is f of u a, and the speed, the flux over here would be f of u b. So this is like an integral form of the conservation statement. So finite volume essentially looks at this form and say, hey, this actually holds true no matter if u is differentiable or not. So why don't we directly discretize this form as opposed to the differential form, which assumes that the solution u is differentiable? Okay, and how do we approximate directly this form? This goes back to our demo. I think we looked at in the beginning of the finite difference lecture. So remember, if I perform a finite difference, what I'm actually approximating, now I'm going to be drawing a function, right? Ooh, my computer is very slow. Okay, so if I draw a function like this, finite difference would only remember the value of the function at grid points. That seems to be the most intuitive way to discretize a function, right? To store a finite number of information about the function, about the infinite dimensional function. But the problem is that it's not so easy to describe. It's not so easy to actually obtain the total amount of stuff within an interval if you only know the value of the function at the boundaries. So instead of finite volume discretization, essentially takes one function. And what it does is that it stores the average amount of material within each interval. So this would be a finite volume approximation. So how does the average amount of stuff in the interval relate to the integral form of the differential equation we are looking at? Can anybody see the relationship between the average over an interval to what we are looking at in the integral form of the equation? Right, so for example, let's say the interval from 0 to 0.1 is the interval A and B. How does this average amount of u, right, within the interval relate to the quantities we are looking at in the integral form?
You could take the difference in the flux and divide it by the the step size to get the average, right?
Yeah, you can take the, well, that's actually you're jumping a little bit ahead. That's actually how you would apply the finite volume method. But like, what is, so okay? So we are looking at the average here, but what is the mathematical definition of an average of a function? Can somebody think of how you would actually mathematically define what the average is?
You take the integral of the function divided by the length of the interval.
Exactly. So you take the integral of this function, which is actually what is here, right? What is on the left-hand side of this the integral form. So essentially, what I'm saying is that I can, another way to write the equation is ddt of b minus a times the average of u within the interval ab, right? So this is actually exactly what the integral is, right? So, and the average is actually what we use to discretize the function in finite volume, okay? That is going to be equal to f of u at a minus f of u at b. When I say a vertical line with a subscript, that's saying the value of this function at a certain point, okay? Or I can just get rid of the b minus a here and divide both sides by b minus a, or the size of this finite volume in this case. Okay, so basically the integral form actually is our finite volume formula. It is saying that the time derivative of the volume average is equal to the difference in the flux over the left and right side of the volume divided by the volume size. Right? Make sense? Okay, so one thing I want to emphasize is that at this point, the finite volume formula is exact. There is no approximation in this whatsoever, right? We discretize the function and obtain this average, and everything here is exact. So what do we need to do to turn this into a numerical scheme?